So I'm going to talk a little bit about regression coefficients and how we interpret the regression coefficients depending on the purpose of the additional variables. So just as a reminder, when we're doing multiple regression, you can test for the relationship of a second predictor with the dependent variable. So what we're talking about here is the difference between simple regression, where all we have is the constant b weight of one predictor and then the score of that predictor to predict y. As we add additional regression coefficients, we're adding additional predictors, and the idea is that we're trying to get better prediction, explain more of the outcome in what we're predicting, the outcome or y, than we would with any one particular prediction. And again, there is no limit to the number of predictors that we can add, as long as each one is providing us incremental validity. Each one's explaining a little bit more of the outcome of y. Now, it's pretty easy to visualize when we simply have a single predictor and an outcome. That's the plots that we've been drawing and the scatter plots we've been talking about for most of this graduate class, both this semester and last semester. But just adding a second variable basically takes us to the limits of what we can easily visualize. So I have an example of a two predictors on an outcome scatter plot. It's kind of a three-dimensional scatter plot, and each data point now is representing both your score on SAT and your number of absences on your grade in a class. So we're kind of creating a little three-dimensional cloud, and a lot of the programs that'll do these for you will actually make it in a rotatable three-dimensional space so you can get an idea of what that relationship looks like. And this is again an example of probably a pretty good relationship, that the combination of absences and SAT combined provide a better prediction for grade than one or the other singularly. But also recognize, try to now add in your mind a third or fourth or fifth predictor and try to visualize that. And that's kind of what I was getting at when we were talking about those residual plots. It really gets to the point where we can no longer rely on a quick glance at a scatter plot to figure out what's going on with a multivariate prediction. And that's why those residual plots are so important, is they don't give us that three-dimensional, fourth-dimensional, fifth-dimensional view of the process, but it does let us know, is there a problem with the prediction? Is there something going on in that multidimensional space that's hard to visualize anymore that means we need to start figuring out where it is? So for example, in this case with two predictors, looking at the graphic up here, we probably can pretty easily predict at least one multivariate outlier. At the very bottom right, you see that little blue dot of 900 SAT, 6 absences with a grade of probably about a 40 right at the bottom. So that's probably a little bit of an outlier, and why it's an outlier isn't any one particular score. So it probably wasn't an outlier in just SAT, it probably wasn't just an outlier in absences, and certainly probably wasn't an outlier necessarily in grades. But when you put the three together, it definitely occupies a space far removed from any other predictions. So just a thing to remember when we're adding additional predictors, recognize that every individual predictor reduces power. It reduces the degrees of freedom, and generally speaking, we want to add a minimum of 10 units per variable as a rule of thumb. And remember that 10 units per variable is per variable entered in the model. So I mentioned this earlier, if you have a categorical variable with 5 levels, which means you're going to have to create 4 dummy codes, that categorical variable doesn't require 10 units. That categorical variable requires 40 additional units. And this is a bare minimum. I would honestly suggest that you consider either getting a program that does power analysis for you, and there's a fair amount of free ones available on the internet, where you basically tell it what is the effect size I'm hoping to find, and it will tell you, ask you how many variables you're predicting with, and it will give you an idea of your power. But I think a general good rule of thumb is to shoot for 20 per variable, not 10. But anything below 10, it's going to make it very hard to find effect sizes. Again, we do need to worry about multilinearity as we add additional predictors. In other words, we're worried that our independent variables are more related to each other than they are the outcome. So that means you're basically measuring the same construct with different variables. You're giving up power for no reason. Not only that, it also has a tendency that when we have highly related predictors, depending on what type of multiple regression we're using, it may actually put the variance in very different places. So we'll often find that models will vary greatly when we use different techniques. And though we expect some variance depending on the technique of data entry that we use, we wouldn't expect large shifts, and that's what we usually find with multilinearity. An example is emotional coping and alexithymia, anxiety and depression. There's a fair amount of variables out there that may be distinct constructs but are very interrelated. And we want to check for that multiclinearity, and we've talked about various ways to test for it, and we will continue to do that also as we move forward into other statistical techniques. So predictive variables can be entered into the model several ways, as I just mentioned. We can enter them all at once, just looking for unique variance explained. We can do hierarchical modeling, entering the variables in blocks. This allows us to examine covariates, nonlinear trends, and interactions. It basically lets us decide the order that we're putting them in, and generally speaking, this is where we hope to be. We hope to be doing hierarchical modeling. We hope to have enough information based on theory and what we're actually researching to be able to say, I first want to enter my variables as individual linear relationships. The second block I want to enter is covariates. I then want to examine nonlinear trends, and then here are the specific interactions I want to look for. Now again, the difference between hierarchical modeling and intermethod also is intermethod is just looking for unique variance explained. So it's a good initial kind of descriptive study of something you're not really sure about based on theory. Hierarchical modeling is explaining all variance in the outcome that is being predicted by your predictors. So hierarchical modeling is going to give you a more powerful predictive model. Intermethod is going to give you more information about the unique variance explained, so it's more useful to kind of identify what are my big predictors in kind of a new setting. And finally, we can move away from entered and hierarchical. So enter, we're just looking for kind of a descriptive idea of which variables are better predictors, not based on theory. Hierarchical modeling, we have theoretical, based on past research, based on logic, reasons to control the order of the variables we're putting in. And then we have basically including based on the strength of the relationship, forward, backwards, and stepwise. Now, again, we're letting statistics take over. We're not telling it what to do. It's doing it based on various calculations that we'll talk about. But the difference between these techniques and enter method is that enter, again, is looking for unique variance. Forward, backwards, and stepwise is trying to explain all variance explained in the outcome. So again, enter method enters all of the predictors simultaneously. All the models are included in the model all at once. Predictors are tested only on their unique contribution to understanding the outcome, the criterion. And the shared variance between any predictors is excluded from all tests. So you're almost always going to get a smaller total model and a smaller prediction model from enter method. And it's not that enter method doesn't have value. I think enter method is a great way when you don't have a lot of theoretical information and you're basically doing initial exploration. If your research question is, I've got 6 predictors, which ones are the best? So you're not necessarily trying to make a model, you're just trying to figure out which ones work well and which ones don't. Maybe you only have the resources or ability to measure a couple of things. So you're wanting to check 6 or 7 things to find out which 2 should I spend money on. That would be a great technique to use enter for. Sequential, hierarchical, is again theory-based. Predictors are added one at a time or in blocks. Regression is computed at each step, but we control the steps. And in here the goals are predictors are being entered early to keep variance shared with predictors entered later. So basically we can be using this to put in variables that we expect or we know we're going to be using based on theory, or even in an applied setting based on reality. Maybe I know I'm going to have to use this first predictor, so let me give it first crack at the variance. It also can allow us to put in covariates. I know there's a gender difference, but I'm not wanting to capture that. I'm wanting to basically account for it and remove it from my prediction because I want to know, broadly speaking, regardless of gender, how predictive is this model. And it also assesses improvement in fit from additional predictors. So we can actually look at the difference between the models that have, for example, only linear terms versus those with the covariate versus those with the nonlinear terms. And finally, we have sequential hierarchical regression, and that simply means that we've turned the decision making over to the computer. I'm sorry, let's back that up. I'm one slide ahead. So sequential hierarchical regression is what we're talking about. Hierarchical regression by its very nature is sequential. So sequential means that the order of entry is being controlled by the researcher. It can be driven by theory, important predictors enter before less important ones, and it also can be driven by practical applications. Like I mentioned, you have an organization that already has a particular predictor that they're not planning to get rid of, and you know that's the base that you're going to build on, but you're trying to convince them to maybe add additional predictors. It allows us to look for nuances, lesser predictors you want to control for, covariates, things that we want to pull out, and we can also look at causality. So, for example, manipulated predictors can be entered before observed predictors. So we can actually take a look and go, the first thing we did was actually a causal study, and we had 3 causal manipulated predictors that were used with random assignment. Let's put those in first, because if we find that relationship, that's a causal relationship. So we can identify those and isolate them as well. So again, what selection methods do we use? How do we decide in what order our blocks put in the sequential or hierarchical method? Generally speaking, sequential or hierarchical is going to be theory driven, and the stepwise forward and backwards is a statistical model. It's computer optimized, and above and beyond enter, it's not just looking at unique variance, it's looking at total variance in the outcome predicted. So if we're trying to arrive at the largest significant R for your predictors, if we're looking for an optimal combination of predictors, and more in applied settings where we're trying to find the very best model, we may want to use these techniques as well. Also, if we don't have a lot of theory behind what we're doing, but we are doing practical prediction, statistical, stepwise, forwards and backwards, makes more sense than enter. So computer optimized includes forward entry, adds predictors one at a time based on the size of the R. So it basically does univariate, bivariate R's for every individual predictor. Then based on the size, it will add the biggest predictor individually first, and then start adding sequentially each next variable, asking does it add to the prediction. And it does this until it finds a change in the R squared is not significant. Now the problem with this is that occasionally it will miss a significant predictor down the line. Backwards entry starts with all predictors in the model, and it removes predictors based on size or bivariate R, and again it stops when the change of R squared, and R squared is the total effect of the model on the outcome, is significant. So when it finds, if I pull this variable out, I don't change the model. I pull this next variable out, I don't change the model. I pull the next variable out, the model just got statistically significantly worse. I put that one back in, I stop pulling them out. Same with forward. I add a predictor, it significantly increases my chance to predict the outcome. I add another one, the model gets better. I add another one, the model gets better. I add another one, the model does not get better. I don't add that one, and I stop. Both of these can result in either forward may miss a predictor, backwards may keep a predictor that doesn't need to be in there. Because you may have 2 variables that have a high bivariate R, but actually are highly related to each other. They're predicting the same thing, but they're at the very end of backwards entry. Or you may have a predictor that's a very small R individually, but the R it predicts is unique and therefore might be missed by forward entry. And that's why we have stepwise. Stepwise does both. It goes all the way forward and all the way back and finds all variables that are predictive. So again, if you're using computer optimized, unless you have a good reason to use forward or backwards entry, usually the default here is to do a stepwise. So again, different entry models can result in different final models. Shared variance assigned according to statistics, not theory. So again, we just have to recognize that if you do a forward, backwards, and stepwise, you may get slightly different models, and sometimes even fairly different models. The larger the difference, so for example, this is another way to find out if there's something wrong with your multivariate model. If you run a stepwise regression, both forward, backwards, and stepwise, and get very different results, that's probably also indicating that there's something else going on in your model that you're missing. You may have multicollinearity somewhere, you may have an interaction that you're not capturing. So this is another way to kind of look for how solid is my model. In a way, it actually harkens back to very early statistics when you may remember back in undergraduate being told check your median, your mean, and your mode, and if all 3 are very similar, you probably have a normal distribution. If they're not similar, that's probably an indicator that you have a non-normal distribution. Likewise, if you run a forward, backwards, and stepwise regression on your data set and find very different models, that's another indicator there's probably a multivariate problem with your prediction. So again, this is useful for exploratory hypotheses, it's useful for data sets with very large number of predictors, and it's also useful for optimal prediction. It is not useful for testing theoretical hypotheses. That's hierarchical. So again, just a quick reminder, standard regression or inter method is looking for unique variance only. It is ignoring any shared variance. It's always going to be probably a weaker model. Sequential, again, if x1 is entered first, it gets all the variance, including the shared variance from x2. When x2 is entered, it gets all the remaining variance it explains, again, including variance explained by x3. And finally, x3 would get the remaining variance. So in this case, we have three variables, x1, x2, and x3, that all explain the same amount of variance in y. And depending which one's put in first is going to give us different responses. So basically, in this particular model, x1 is our biggest predictor, x2 is our second biggest predictor, x3 is our weakest predictor. But if we actually enter these ourselves in a hierarchical regression, we might find the exact difference, or a different response. We might find that x3 is the biggest predictor, followed by x1, followed by x2. Now also think about if x1 and x3 were allowed to get variance first, there wouldn't be a lot left for x2, and x2 might actually be found to be non-significant. And that's an example of the next model. So in this case, x1 and x3 are given first crack in a forward regression, and x2 may actually be seen as a non-significant predictor. So again, predictability, multiple regression can create equations to predict outcomes. More predictors tend to result in better predictions. So example, if all we're doing to predict alcoholism is emotional coping, it's probably not going to be quite as good as predicting alcoholism from emotional coping, attentiveness, and family history. As we add each one, now notice, let's take a quick look at those equations. Coping actually predicted a little bit more of alcoholism when it was allowed to predict alone. So again, our B weight is 0.75. So every one level of cope was predicting 0.75 increase in alcoholism. In the bottom model, the model with more items in it, the multivariate model, it's now 0.65. It's a slightly weaker relationship because some of the variance it was explaining is now being given to attentiveness and to history. But overall, the model is now more predictive. So again, briefly, just higher order trends. Again, we can do nonlinear trends. If we're looking at curvilinear data, so one bend, we create it by squaring the predictor. If we have data that looks like it has two bends in it, we'd create a cubic term, raising that predictor to the power of 3. And again, it's basically just raising it by the number of bends. So if you've got 3 bends, it's a quartic relationship. 4 bends, it's a quintic relationship. So again, we'd raise it by the power of 4, raise it by the power of 5. So a general rule is you're raising it to the power of 1 over the number of bends you expect to see. So if you expect 2 bends, you're raising it to the power of 3. You're expecting 3 bends, you're actually raising it to the power of 4, and so forth. Again, if we have a categorical variable, nominal variables, if it's dichotomous to begin with, we don't have to do anything to it. If it has more than 2 outcomes, in other words, it has more than 2 levels, 3 or more, we're going to have to create dummy codes. And the number of dummy codes is the number of levels minus 1. So for example, if we have a categorical variable with 5 levels, 5 minus 1 is 4, we're going to have to create 4 dummy codes. And the reason we're only having to create 4 is that by the very nature of dummy codes, each dummy code represents either there or not there. So if you have a combination of all 4 dummy codes being not there, 0, 0, 0, 0, that is your 5th condition. So ordinal variables, how do we treat them? So with a nominal variable, it's quite clear. If it's nominal, if it's categorical, we have to create dummy codes. Or if it's only 2 levels, treat it as a dichotomous variable. If it's an ordinal variable, we have to make a decision. We can usually treat it as either nominal or continuous. So the larger the range, the more numbers are in that ordinal variable, the more we may actually be able to look at it as basically continuous or ratio data. What we want to look at, though, is, again, is it normally distributed? Ordinal data often is not. We may have to do a transformation. However, if there's a small range, so if we have ordinal data with 5 or less, 4 or less, definitely 3 or less categories, probably at that case, we're going to treat it as a categorical variable and create dummy codes. And again, we may have to play around a little bit to see what is most appropriate for this particular ordinal variable. How should we treat it? So again, this is just a quick example of dummy codes, and remember that whenever we're looking at a dummy code, we're putting those dummy codes in a single block. So we should not be mixing dummy codes with other variables. So when we create dummy codes, honestly, we probably should be doing a hierarchical regression. We should be in control of the situation. Because in order to be able to interpret the dummy code, we need to look at the constant in the model. Because the constant is, remember, the constant is that A. Constant is what if all variables are 0. Well, since we're creating 1 or 0 variables, the condition, the constant where all is 0, is the one thing we didn't code for. So for example, if we're coding, B for constant represents the mean of the category coded as 0, 0. So in this case, for example, if we're looking at Edwardsville versus Belleville versus Webster Groves, we have our first dummy code, which is 1 if you're from Edwardsville, 0 if you're from anywhere else. We have our second dummy code, which is 1 if you're from Belleville, 0 if you're anyone else. And that means that if we have a 0, 0, that means they're from Webster Groves, and that's the constant. So the constant is whether or not there's a significant relationship with that category. So again, we're going to use these dummy codes to bring a categorical variable into a multiple regression. Why would we do this instead of simply doing an ANOVA? Most likely it's going to be done when we have a combination of categorical and continuous variables. And we can't have continuous variables as a prediction in an ANOVA unless we convert them to a categorical variable. And that actually is a problematic in itself. Generally speaking, if we have continuous variables, we want to leave them alone. If we have categorical variables, we want to be able to look at them as well, and probably the best of both worlds in that case is I would rather see you go to a multiple regression, keeping your continuous variables continuous if you also have categorical variables, than trying to force continuous variables into categories to allow you to move to an ANOVA.